Hello, my name is Shahriari, and this is a lecture in a series of lectures on elementary abstract algebra based on my book, Algebra in Action, a course in groups, rings, and fields. This particular very short lecture is some elementary applications of group theory to number theory. The main point is that you can use group theory to prove number theory results. Now, there's deep connections between algebra and number theory, which is not the subject of this lecture. So as an example, let's say that n is a positive integer. We have proved that all cyclic groups of the same order are isomorphic. So for each order 5, there's one cyclic group. For order 17, there's another one. For order 25, there's one. And z mod nz, the integers mod n, so that would be 0 through n minus 1, where the addition is modular addition. You add as usual, but then the sum is going to be the remainder when you divide by n. That's a cyclic group of order n. One notation, phi of n, the Euler phi function, is the number of integers between 1 and n that are relatively prime to n. Greatest common divisor with n is 1. The number of those is phi of n. One fact that we have proved in group theory is that the cyclic group of order n has phi n generators. In fact, every integer between 1 and n that is relatively prime to n will generate z mod nz. What does that mean? That means that if you take that element and just keep adding it to itself, you will get every element of z mod nz. That's one fact from group theory that we know. Another fact from group theory we know is that if you have two integers that are relatively prime to each other, n and m, where their greatest common divisor is 1, then the direct product of the cyclic group of order n and the cyclic group of order m is the cyclic group of order nm. This actually follows from our third fact, which says that if you have any group H and any group K, and you have one element in one and one element in the other, we are all talking about finite groups, then the order of pair AB in the direct product of H cross K is made up of, its elements are pairs of elements, where the first element in the pair is from H and the second one from K, and the order of AB in that is the least common multiple of the order of A in H and order of B in K. And so why does fact 2 follow from fact 3? Well, if the greatest common divisor of two integers is 1, then the least common multiple is their product. If you make a pair of elements, one a generator from z mod nz and another one from z mod mz, then you will get an element of order nm, and that will be a generator for your resulting group, and that will be cyclic. And why is the order of AB the least common multiple of order of A and order of B? Well, because when you take AB and keep multiplying itself, when will you get identity in both coordinates? Every order of A powers, you will get an identity in the first one. Every order of B powers, you get an identity in the second coordinate. And the first time you actually get an identity in both coordinates is the least common multiple of order of A and order of B. The facts that I said are all elementary group theory facts that we have seen before. Follows from that little number theory fact that the phi function is multiplicative. So phi of nm equals phi of n times phi of m, as long as n and m are relatively prime. Why does this follow from those facts? Well, because phi of nm, what is that? Well, that's the number of generators of the cyclic group with nm elements, okay? And that cyclic group is isomorphic to the cyclic group of order n cross the cyclic group of order m, and its generators are exactly, by fact 3, pairs of generators, one from znz and one from zmz. And the cyclic group on n of order n has phi n generators. The cyclic group of order m has phi m generators. So to make it a generator for the cyclic group of order nm, you take one of these and one of those, and how many choices do you have for that? Phi of n times phi of m. So both of sides of this equation are counting the number of generators for a cyclic group of order nm, and so they're equal. So you can prove this directly without using any group theory, but the point is that if you're familiar with group theory facts, you can prove number theory facts as well. So actually, the main purpose of what I want to talk about in this lecture is to use Lagrange's theorem and its corollaries to prove a number theory fact. So what was Lagrange's theorem? It was that if you have a finite group and if you have a subgroup less than or equal to H less than or equal to G, means H is a subgroup of G, then the order of H, the number of elements in H, can't just be willy-nilly anything. It has to be a number that divides the order of G. Okay, so what? Well, a corollary to that is that if you take an element of a group and then its order divides the order of the group. And the reason for that is that if you take that element and you look at the cyclic subgroup generated by that, that cyclic subgroup is a subgroup of the whole group. And so its order divides the order of the group. But the order of the cyclic group generated by an element is the order of that element, the order of an element being the first time that you get identity when you raise it to powers. So order of every element divides the order of the group. And a corollary to that is that if you take any element and raise it to the size of the group, if n is the size of your group, then you always will get identity. Why is that? Well, because the order of A is a factor of the size of the group. So n, the size of the group, is order of A times k. And so when you take A and raise it to the power order of A times k, that's raising n to the power order of A, and then taking that, raising the power k, but n to the power order of A is already identity. Raising to the power k will not do anything and gives you identity again. So we want to apply that to the group of units of Z mod NZ. So what's the group of units of Z mod NZ? We saw Z mod NZ with addition as a cyclic group of order n. But if you look at multiplication mod n, you take two elements and multiply them, and the result is going to be the remainder when you divide by n. Now, if you look at all integers between 0 and n minus 1, you will not get a group. But if you pick the invertible ones, the ones that are invertible under multiplication, then you do get a group. And that's the group of units Z mod NZ. And this is a group we have seen. Sometimes it's cyclic, sometimes it's not. But it is an abelian group. We proved that actually the elements of this are exactly those numbers between 1 and n that are relatively prime to 1. Those are exactly those numbers that have an inverse under multiplication mod n. And so the elements of Z mod NZ are exactly the generators of Z mod NZ under addition. Those are all integers between 1 and n that are relatively prime to n. Now, this is an abelian group of order phi of n. Phi of n was the number of generators of Z mod NZ, and so that's the same as the number of elements of Z mod NZ, the units in Z mod NZ. So what by Lagrange's theorem, now we know that if you take anything, any element of this group, and you raise it to the order of the group, you get identity. And the identity in the group of units is just one, in the group of units under multiplication is just 1. So we get that a to the phi n equals 1 in that group. But if you now translate that from what does that mean to take a to the phi n and you get 1? Well, what that means is that if you take a and raise it to the power phi n, but then find the remainder of that when you divide by n, you get 1. And from that, we get this version of Euler's theorem, that if you pick something in Z mod NZ, the units of Z mod NZ, so if you take an integer between 1 and n that's relatively prime to n, then if you raise that to the power phi of n, you get remainder 1 when divided by n. This is called Euler's theorem. And in particular, if instead of n, you take a prime p, then the number of integers less than it that are relatively prime to it is p minus 1. So phi of n becomes p minus 1 if n is p. And instead of saying that you want a number a that's relatively prime to n, all you have to say is that that 1 prime doesn't divide it. So if p is a prime, you pick a number a between 1 and p does not divide a, then a to the p minus 1 has remainder 1 when divided by p. And this is a version of Fermat's theorem. Now, the only little thing that I should say is that in the way I've said it, I don't actually need to say a is between 1 and n in Euler's theorem, or a is between 1 and p in Fermat's theorem. That's not really necessary. Although, when you think of it in terms of group theory, you have to say that because you want a to be an element of these groups. But you can get rid of that with a little bit of number theory, not really number theory, but working with congruences. You can get rid of the fact that you need those, and I will walk us through that. But the point is that the main argument can be just done very cleanly using group theory. This last thing, Fermat's little theorem, has many different proofs, but this probably is sort of the quickest one. Okay, so now, so I'm going to repeat now what Euler's theorem is, and I'm going to take that superfluous assumption out. So a is an integer, and n is a positive integer. Assume that a is relatively prime to n. We need that. Then, when you take a and raise it to the power phi n, it has remainder 1 when divided by n. This has nothing to do with group theory. This is, I mean, It does, as we saw, but at least the statement is completely a statement that doesn't talk about groups. It's just about integers. And one way to write that is to write that a to the phi n is congruent to what mod n. And all that means is that a to the phi n and 1 have the same remainder when you divide them by n, which is the same as saying that a to the phi n has remainder 1 when divided by n. Okay, now how would the proof of this go? We basically did the proof, but I'm just going to remind you, but this time I'm going to say it again, but this time I'm not assuming that a is between 1 and n. So to take care of that little snafu, I will take the remainder of a when you divide it by n and call that u. So u is the remainder of a when divided by n. So that means what? That means that a is nk plus u. Now, if you think about that for a second, or if you know about congruences, or if you read my book or watch the video about congruences, then you will know that a times 2 phi n has the same remainder as u 2 phi n. So if u and a have the same remainder when divided by n, so do a to the phi n, a to the any power, and u to any power. And that's not very hard to see. So because if you divide a by n and get remainder u, that means that a is nk plus u. So what will a squared be? A squared will be nk plus u times nk plus u. If you multiply that using the distributive law, every term would have some factor of n except for u squared. And so the remainder of a squared and a squared when divided by n, everything is already divisible by n, except possibly u squared. So whatever the remainder of u squared when divided by n is the same as the remainder of a squared. And you can repeat that. A cubed has the same remainder as u cubed and so forth. And a to the phi n will have the same remainder as u to the phi n. And then u is an element of z mod nz. It's a unit in z mod nz. It's between 1 and n. And because a was relatively prime to n, so will be u. And so u will be in z mod nz, a unit is z mod nz. And then by Lagrange's theorem, because the number of elements in that group is phi of n, then if you take u to phi of n, you get 1. And that's the proof, because if u to the phi of n gives you 1 in z mod nz, so does a to the phi n, and you get a to the phi n equals 1 mod n. So here I did use a few little facts about congruences that I didn't write down. And again, if you watch the video on congruences, I will go over those. These are sort of elementary congruence things, but the basic idea was the group theory one. And the corollary of this is Fermat's little theorem, that if you have an integer and if p is a prime and p doesn't divide a, well, then that means that p and a have greatest common divisor equal to 1. Then a to the p minus 1 has remainder 1 when divided by p, and we write that as a to the p minus 1 is congruent to 1 mod p. That's exactly what that means, that the remainder of a to the p minus 1 and 1 when divided by p are the same. And so, for example, as an example, without doing any calculation, you know that 10 to the 46, if you divide it by 47, will have remainder 1. There's another way of writing the Fermat's little theorem. If you don't like that condition, p doesn't divide a, then you say if p is a prime number and if a is any integer, then a to the p is congruent to a mod p. And you prove that by doing two cases. You say either p divides a or p doesn't divide a. If p divides a, then a to the p is divisible by p and a is divisible by p. So the remainder of both of them is 0 when you divide it by p. So a to the p is certainly equal to congruent to a mod p. If p does not divide a, then by the previous version of Fermat's little theorem, this one, a to the p minus 1 has remainder 1 when divided by p, but then a has remainder, so then it has the same remainder as a when divided by p. So if you multiply those, you multiply a by both sides, you get that a to the p has remainder a when divided by p, or has the same remainder as a when divided by p. And so again, that follows from those basic congruence properties. Now, so this is the end of this lecture, but the moral of the story is that Fermat's little theorem has many, many different proofs, very nice proofs. Some of them use elementary number theory. There's one that uses dynamical systems. There's all kinds of different proofs for Fermat's little theorem. But this one brings home the idea really clearly. Why is a to the p minus 1 congruent to 1 mod p when a is an integer and p is a prime and p doesn't divide a? Well, the reason is that if you look at the group, if you look at the units in z mod pz, there's p minus 1 of them, and they form a group. And so, and it's a group of order p minus 1. And if you take any element in there and raise it to the size of the group, you get 1. So A, you take any element in that group A and raise it to p minus 1, you get 1. Now, what if A is not in that group, meaning that it's not a number between 0 and p minus 1? Well, it's congruent to something in there, and raising either one will give you the same answer, and therefore you have 1 mod p. That's a very conceptual, clear proof based on group theory. Till next time.